R1 of u and R2 of u, and then R3 of u. Also, you have this vector field is given everywhere in 3 space, and it's given by its coordinate v1 of x, comma y, comma z, v2 of x, comma y, comma z, and finally v3 of x, comma y, comma z. And now you're able, with these quantities here, now you're able to give the formula for the tangential curve integral. You have here that this is the tangential curve of v along the curve kr, and it's the general formula for this is kr, and then it's the dot product between v and the tangential unit vector. And when you have to unfold this, then you have to take the integral with this parametric representation, the integral from a to b of the restriction of the vector field to the parametric representation, r of u, and then you should multiply by the tangent vector, and this is the derivative of the parametric representation du. So in this sense, you have changed the curve integral along the curve into an ordinary integral which you can compute. And now I'll discuss a special case here. So I say if R of A is equal to R of B, and that is when the curve is closed. I could write here then KR is closed. And the tangential curve integral, this is this one, is called the circulation of the vector field V along KR. Sometimes you, in order to illustrate or emphasize that this is a closed curve, you put a small circle on top of this KR. And also it is denoted, the circulation of V along the closed curve KR. And normally you, when you write the integral, you put a circle on top of the integral, also to indicate that this is a circulation. Now, another special case is that this is if the vector field is a gradient vector field. And that is a function f exists such that v is equal to the gradient of f, and remember the gradient is the partial derivatives of f with respect to the three coordinates, like this. Then, or I should say, just take this away. Then the tangential curve integral of v along kr is the functional value in the endpoint of the curve, or in the endpoint. Again, I'll just take this away. And the endpoint, that is r of b, minus the initial point, like this. I should, this is wrong. I better write it correctly. This is f of rb minus f of ra, like this. And we call f the indefinite integral of the vector field v. So when is a vector field a gradient vector field? If the vector field is defined in a star-shaped region, and the curl of v is equal to the zero vector, then v is a gradient field, or gradient vector field. And what is a star-shaped region? A star-shaped region is a region where there exists a point where you can reach all the points by a straight line. So if this is the case, then for instance, the whole of R3 is star-shaped, of course. Then, and the curl of V is 0, then V is a gradient vector field. So this is the first example that I would like to show today. The next, or the first, say the first integral theorem. The next integral I want to look at is the flux integral. The flux integral And here you have the flux through a surface. So let me define the surface. I have here a surface, you know, it's described by two parameters. Here I call them u and v. And u varies between a and b. And v varies between c and d. So it is simply this rectangle here. It's a square, apparently. But this is mapped. This is mapped onto a surface. So let me, in 3 space, so I have my coordinate system, x, y, and z. And then I have a surface, say, like this. I call this surface F, and I indicate that it is given by this parametric representation. On the surface, you have a normal vector. Say if this is, then you have a normal vector that is perpendicular to the surface. Let me call this, and this is a unit vector. This was not very good, but it's called n, and I indicate this is still not very good. So I indicate that this problem with writing small n's, this is n. So this is the normal vector, and also you have at any point in space, and in particular on the surface, you have a vector field. Now, again, you have your parametric representation. This is R1 of u comma v, R2, no, it's not, R2 of u comma v, that's the second coordinate, and the third coordinate, R3 of u comma v. And u is in the interval from a to b, and v is in the interval from c to d. Then the flux. The flux of the vector field through the surface, f of r, is the integral over the surface of the vector field times the unit normal vector and then you have the integration parameter. And now when you have the parametric representation, then you can unfold this integral as a double integral. It's from a to b and from c to d of the restriction of the vector field to the surface. That is, you evaluate the vector field for the parametric representation like this, and then you dot it with the normal vector, and the normal vector to surface given with this parametric representation is simply the derivative of the parametric representation with respect to the one parameter, and then it is crossed with the derivative with respect to the other vector, and you integrate it with respect to u and v. So this is the flux. Further on, I would like to introduce to you the volume integral. Or introduce this repetition. And in the volume integral, you have three parameters in order to describe your volume. Let me illustrate this as follows. You have say here your parameter space u, v, and w. In this parameter space, you have an axis parallel figure or parallelepipedium. So it looks something like this. And if you call this for A, then you could write A as the set of points in 3 space for which U belongs to A, B, V belongs to C, D, and W belongs to E, F. So this is mapped onto a figure through this mapping here, R. And let's say that it is mapped onto this solid region in 3 space. You have your coordinate system, X, Y, and Z. And just to indicate that this is a 3-dimensional figure, I take such a line here. We denote this solid region for omega and indicate that it is with the parametric representation R. So this is a solid region. And the boundary of this region is denoted D omega R. And this is the boundary of omega R. Okay. If in addition we have a function which is defined on omega R, so it's a mapping, so to speak, of omega R onto the real numbers. Then this volume integral, and we integrate over the solid region, and we integrate F This is equal, when we unfold it with our parametric representation, it's a triple integral, and we have to take the restriction of the function f to the parametric representation, u comma v comma w. And then we have to multiply with a Jacobian for the parametric representation. So, and this will be the numerical value of the determinant of r prime u, that's the first column, r prime v, that's the second column, and r prime w, third column. And then I end the numerical sign, and then you integrate with respect to u, v, and w. And you see the integration in u goes from a to b, and v from c to d, and finally w from e to f. Again, we have a special case, and this is if f is equal to 1, then you have that the integral here is 1 and then times d mu. And this is simply the volume of your solid region, like this. Now, let's see, we have a special case where we can actually use this. So let now we have V is a vector field, and it has three coordinates, V1, V2, and V3. And each of them are, of course, functions of x, y, and z. So let this be a vector field then the divergence of V, that is dv1 dx plus dv2 dy plus dv3 dz is a function. See, this is a scalar variable, so this is a function, and then it is a possible f, it's a possible f in a volume integral. So if we compute the divergence of a vector field, and then we can take the volume integral of this divergence, then what do we get? And here I have, I can write here, if this is the case, then Gauss's theorem applies. So it says that the volume integral over the solid region of the divergence of the vector field is equal to the flux of the vector field through the boundary of the solid region. Like this. Okay. I'll continue now with Stokes' theorem. So let me just take you through this. Stokes' theorem. And I'll just make a small sketch. Stokes' theorem, it works with, say, a surface. Just show it like this. I have a surface. I call this surface F, and it has a parametric representation. And then the boundary of this surface is called dF. This surface, again, at any point, has a normal vector. Let's see, it's in this direction here. So a normal unit vector, n of f. And then also you're looking at a vector field. Now, I should say that df of r has an orientation or direction such that the right-hand rule is fulfilled. And it's simply, if you look at it, then if this is a direction, this will fulfill the right-hand rule. And the way I remember it is that I take my right hand and then I put the four fingers in the direction of orientation of the boundary, and then the thumb should point in the direction of the normal vector. That's the way to remember this. So then the circulation of V, of the vector field V, along the boundary of the surface is equal to the flux of the curl of V. That is the curl flux V through this surface. Remember the curl of V, that's a vector, and it is the cross product between the Nabla operator I'll show you this in an example shortly, and the vector field B. So in this sense, you have that the circulation, which is a one-dimensional integral, is equal to the flux. What you should remember, though, is that this works for any surface that has df as the boundary. So it's not unique in the sense that you have a given f. You can, in fact, choose any f that has df as the boundary. I'll demonstrate that in an example to come. So now I will, before the break, I will give you an example. And and it's an example on Stokes. But let's see, we have here our surface, and it's a simple surface. It runs from 1 to 3 in the y direction, and it runs from 1 to 3 in the x direction. This means that it is this square here, and the vector field I'm looking at is yx, and then y, and then x squared. Now, if I want to compute the circulation, then I will compute the circulation in the positive direction, that is counterclockwise, as seen from the top of the z-axis. In order to do so, I need to parameterize this boundary, and it's consisting of 4 parts. So if I call this part 1, and this part 2, part 3, and part 4, then I can write the I parameterize now, and if you have 1, then you have that that the parametric representation, it's a function of the variable u, and you can see only x changes along this this boundary. We are in the xy plane, so z will be 0 and y will be equal to 1. And if you look at x, it varies from 1 to 3, and you can write this in the following way: 1 plus 2u. And in this sense, then u belongs to the interval from 0 to 1. When u is 0, then our 1 is 1, 1, 0. This is this point. And when u is 1, then you have 3, 1, 0. Well, similarly, if you take the second, again, we use u as the parameter. And here, x is constant. X is constant, equal to 3. Z is still 0. And now it is y that varies as 1 plus 2u. U still belongs to the, and so on. You can, in this way, you can parameterize all four parts of this boundary, and then let us write or determine a tangential curve integral along the first boundary. This is from 0 to 1. And then you need your vector field. And if we just go back, and look at, we have the vector field here. It's yx, y, x squared. And you need to put in your parametric representation into the vector field. So you have y is 1, so it is 1 times 1 plus 2u. And then y is equal to 1. And then you have x squared, that is 1 plus 2u squared. So this is the vector field. And now you need the derivative that is you need r1 prime of u, and this is simply 2, 0, 0 when you take the derivative of this. So this should be multiplied by 2, 0, 0 and integrated with respect to u. When you do this dot product, you end up with an integral from 0 to 1 of, you simply only get the first coordinate here, so you get 2 plus 4u du, and this will be easy to integrate. You get 2u plus 4 divided by 2u squared, and this should be taken between these limits. Nothing from the lower limit. From the upper limit, you get 2 plus 2, that is 4. And so on. You should compute then the tangential curve integral of v with respect to 2, and so forth. And then you can finally find the circulation of your vector field along the boundary, f as the tangential curve integral of v with respect to 1. That was not very nice. So 1. And then plus the tangential curve integral, and so forth. So it's fairly easy to do it, but it's a bit tedious. Is there a better way or an easier way that we can do this? Yes, we can use the Stokes theorem. Let's see how that works. So I write here, I want to use Stokes. And then I have the boundary. I need to have what is called the spanning surface. let's go back and look at it. If I take this one, so this is the area, or this is simply the closed curve, and I could choose any. Surface that has this curve here as the boundary. For instance, I could take a pyramid where this is, and the top is at the set level 5, and then I could use this surface, but this would be as tedious as the one I'm doing now. So the simplest thing to do for the spanning surface is to choose the surface that lies in the xy plane. And then it's fairly easy to write down a parametric representation for this. I call it R, and it has two variables. Now it is now it's a surface. It's simply, I can choose the two variables u and v, and u belongs to the interval from 1 to 3, and so does v. So this is simply, this was fairly easy. But what we also need in order to use the Stokes theorem, let's go back. I'm going to compute, say, the circulation as the flux of the curl of V. So I need to compute the curl of V. Let's do that. I take the curl, which is a vector, and this is simply the cross product between the gradient d dx, d dy, and d dz of my vector field. And as I remember, it's y comma x, y, and then x squared. So if you do this, then you compute it in the normal way. You get this times this minus this times this, and this will be, this doesn't depend on y, and this doesn't depend on z. So so this will be 0, and then the next one will be, it will be this times this minus this times this, and this will be minus 2x. And then finally, you have this times this minus this times this. And this will be, this doesn't depend on y. And then you get minus x for the last one. Let me just take these away and I re-establish this one, and this one was, as I recall it was y. Okay, now we have the curl of our vector field, but we also need the normal vector in order to apply, or in order to compute the flux. So I compute, this is, if you see here, you have that, this is a parametric representation, so I get 1, 0, 0, and I get 0, 1, 0. And when I compute this cross product, I get simply 0, 0, 1. Well, you would expect that. It's a normal to the xy plane, so that will be in the direction of the z-axis. And now we are able to compute the circulation. And it's a circulation of V along the boundary of this surface. And it's, when I use Stokes, it's equal to the flux of the curl of V at this surface here. So it will be the integral of the restriction of this curl to my parametric representation. And you see the curl, we have it here. So I only need to input x, which is u. So I get 0 minus 2u, and then minus u. And then I need to dot it with my normal vector, and I should integrate in the two parameters from 1 to 3 in both parameters, du, dv. So this is a double integral that I need to evaluate. So I get from 1 to 3, 1 to 3. And then the dot product here is simply minus u, du, dv. And this is equal to say the integral from 1 to 3 of minus 1/2 u squared. And this should be taken between 1 and 3, and then dv. So this integral here, it will be minus so it will be minus 9/2, and then minus minus plus 1/2. So this will be minus 4. I can put this outside the integration with respect to dv. So, and the last integral here is equal to 2, so it will be minus 4 times 2, and that is minus 8. So in this way, by a single integral, you have computed the circulation. Sometimes it's advantageous to use just to use the Stokes theorem in this direction, as I've done here, and that is when it is cumbersome to compute the integral along the boundary. And sometimes it's more advantageous to do it the other way around. So I think with this, we'll have a break until 10 minutes past 11, and I'll give you the second part of the lecture.